Yeah, looks good.
Yeah, cool. Great. So I wanted to just give a talk today about how we do neutral diffusion in MOM6. So this was a project that I did when I was at GFDL, and much thanks and appreciation to Bob, Alistair, and Steve for kind of taking me under their wing and trying to help me understand the problem and implement something new. So some of this builds on some of the material that we've been talking about. Oddly enough, with the regridding and remapping part of it, where we apply some of those same concepts and ideas to this problem of horizontal diffusion. So hopefully this was kind of one of the ways that I figured out how the regridding remapping was going on. So part of this is going to be my exposition of what it means to do a reconstruction in the vertical and do some application of that. So just really briefly, I know that many of you understand that one of the big problems in ocean modeling is how you actually capture the effect of mesoscale eddies. So one of the things, though, that we need to be careful of when we talk about what are we actually parameterizing is the effect of is whether we're talking about mixing, whether we're talking about stirring, are we talking about enhanced viscosity, what we're talking about. So for the problem of neutral diffusion or kind of lateral or horizontal diffusion, in general, what we're talking about are this idea of an eddy deforming a tracer field. So there's the picture or the diagram on the right is a very famous one. I think at this point it's 65 years old, but it's still one of, I think, conceptually one of the easiest ways that I think of why we think that eddies might actually contribute to enhanced diffusion. So shown on the right-hand side is just this is a low pressure eddy, and there's a checkerboard pattern. That's just been superimposed onto that. And the evolution of this checkerboard pattern as it gets affected around in this flow field that's caused by this eddy, you can see that it begins to stretch out, right? So it goes from this nice square checkerboard, deforms, and starts to filament. So that filamentation tends to actually sharpens the tracer gradients, right? And so when you sharpen a tracer gradient, then you can actually get a larger flux because at the molecular level, because you have a sharper gradient. And so this is kind of more formalized by the Boost-Nesk hypothesis, adapted for tracers. The Boost-Nesk hypothesis originally was intended more for viscosity and the mixing of momentum by turbulence, but it essentially says that you can model the effect of turbulence as an enhanced down gradient diffusion. So that's kind of the thing that we're talking about today. Specifically in the ocean, this mixing happens along the direction of neutral buoyancy, right? So we know that processes in the ocean tend to be adiabatic. And so originally their thinking is that mixing happens along an isopycnal direction. Later on, there's been a lot of literature that talking about, okay, isopycnal is not truly neutral in the sense that that true neutrality means that there be no buoyancy flux. I'll get into that a little bit later, that distinction, but for now, just think about the idea that we don't want to diffuse along the surfaces of the model, which can be, as Alistair, Steve, and Bob were talking about before, we have MOM6 is a general coordinate model, so we're not guaranteed that the surfaces of the model, the layer space of the model, is isopycnal or not. And especially for a model like POP or other Z star models or Z level models or sigma models, you have to do some type of rotation if you want to orient the diffusive fluxes along an isopycnal. So this has been done for quite a long time. One of the things that this is also called is Reddy type diffusion, and that was because Reddy back in 1982, she kind of formalized the tensor form of the algebra and showed a way that you could calculate the fluxes by rotating the diffusion tensor along these isopycnal directions. So from the coordinate of the model, rotate the diffusion tensor so that you have not just horizontal diffusive fluxes, but also vertical fluxes, and that those two together are oriented along an isopycnal plane. Cox 1987 showed that in a global model that this generally improved model skill, but they still needed background horizontal diffusion to do some kind of diapycnal mixing. And later on, this was kind of recognized that the need for this background horizontal diffusion was done away with by Gent McWilliams, which is a different part of a tracer effect. So then Griffiths-Oil 98 came along and proposed a way to calculate this so that there was no net buoyancy flux, and to discretize the operator itself to ensure that tracer variance reduces everywhere. right? So this is what diffusion tends to do, right? You never want to sharpen a gradient; it always diffuses gradients, which leads to a reduction in tracer variance. And then there's been a series of papers, probably one of the more recent ones, that show that the way that you calculate slopes, typically what was done in these implementations was that they used a local estimate of what the isopycnal slope was, or the neutral tangent plane. But Groskamp and all really identified a nice way to show that you can actually get an accuracy with that. So the equation on the right-hand side, is just some basic terminology and notation. So this tensor operator kappa sub rho is just the long isopycnal diffusion operator. The next set of equations, this kappa small, is what happens if you assume that isopycnal slopes are small, or neutral tangent planes are small. And the last one is probably the one that is actually much more germane to the conversation that we're talking about here, where we're essentially saying, okay, you have a diffusion of temperature and you have a diffusion of salinity. So if you compare the buoyancy gain or loss by those by multiplying them by the thermal expansion coefficient and the halon contraction coefficient, respectively, you generate a necessary condition for a no net buoyancy gain or loss due to the diffusion of temperature and salinity. And so that's what that third equation right there is just essentially saying, is that the buoyancy gain or loss due to the diffusion of temperature has to be equally balanced by the buoyancy gain or loss by salinity, by the diffusion of salinity. So there were a couple of papers in 1998, including the Griffiths paper that I mentioned, that showed some problems with the rotated tensor approach. So one in particular showed, Bleckers et al. In 1998 showed in particular that no local rotated tensor scheme can be guaranteed to be positive definite. So this actually is a big problem, because it means that you can actually get new extrema in your tracer field if you try to do this rotated approach. And we know that diffusion, like I said, wants to reduce tracer variance. Griffiths 1998 also demonstrated that the original ready operator is also susceptible to an instability. So if you look on the figure on the right-hand side, this instability shows up after, I think, something like 1,000 years of integration. But you can see that instead of having a nice smooth thermocline, you actually get these jags in the northern part of the basin, around 60 degrees north, in that top panel. He also, like I said, made some good thermodynamic arguments about how you can actually calculate explicitly a no net buoyancy loss. And so his modifications to the algorithm are shown in the bottom panel there. And you can see that, especially in the 60 degrees north, where you have these strong steeping isopycnals, that you get a much smoother thermocline, as opposed to the top panel, where you have this kind of noise within the thermocline. One key other point is that when you're calculating a slope, right, a slope is just simply a change over a horizontal distance over a change in a vertical distance. So what happens then, if you have very unstratified regions, you get very large slopes. And so for numerical reasons, those slopes need to be tapered and limited. So this happens near the boundary layers quite a lot, or it can also happen in regions where the ocean is weakly stratified, like the Southern Ocean, parts of the Arctic Ocean. So it's something that's necessary for numerical reasons, but it has no physical justification whatsoever. And so there was a nice paper by Anand Gananandeskin in 2007 that showed that there's actually some, this purely empirical, not physics-based choice can actually lead to changes in precipitation and changes in the vertical structure of heat uptake. So it's a climate scale response to something that's completely arbitrary. So for those reasons, we wanted to come up with a way of doing something completely different from a rotated operator approach that solves some of these problems. So the main goals of this is to create a new discretized epineutral diffusion operator, epineutral meaning being along a neutral direction, that is suitable for a general coordinate model, so it can work in any arbitrary coordinate, that preserves the extrema so that you don't get new values, new maxima in your field, or minima, and it has no need for this regularization or tapering of the slopes. So the way forward, and this is basically the gist of the talk, is that we've come up with this way to calculate neutral fluxes within a refinement of the space between two columns of a model using high-order polynomial reconstruction of tracers. So that's a very dense, very jargony kind of summary of it. And so my goal for at the end of this presentation is that we can we'll unpack some of these specific jargony kind of things, and hopefully give you a nice idea of visual idea or conceptual idea of what we mean by this statement right here. So just a quick note and an advertisement for the next series of talks. So epineutral diffusion is appropriate for the adiabatic interior ocean. So there are some arguments that have been made that eddy fluxes are not actually epineutral in the boundary layers. That's both in the surface boundary layer or near the bottom boundary layer. So Gustavo Marquez is going to be talking in the next set of sessions for how to deal with this, for how to deal with diffusion at these surface and bottom boundary layers. But specifically for this talk, we're assuming that all the neutral fluxes are always, or all the eddy fluxes are going to be perfectly neutral. Okay, so Bob, Alistair, and Steve spent a little bit of time talking about polynomial reconstructions that underpin the regridding and the remapping that happened in MOM6. So for here, this is the way that really helped me visualize it. So we start from recognizing that a tracer concentration in a finite volume model like MOM6 represents just a cell average and represents a cell average, right? It's a single concentration that spans the entirety of that finite thickness that that a layer contains in the model. So when we talk about these kind of polynomial reconstructions, we're talking about generating something that's in between those things. So if you looked at it purely in layer space and just took that statement that a tracer concentration is a cell average in a vertical discretization, you have what we call a piecewise constant representation of a tracer in the vertical. So that's kind of shown here on the leftmost panel, the leftmost column, where if you just plot that temperature then, right, you get these very large jumps where you have just the changes in a layer, right? And that represents actually a physical system that is full of hydraulic shocks. And as we know, especially in the quiescent deeper part of the ocean is not hydraulic, does not have these big hydraulic jumps. So what these polynomial reconstructions allow us to do is to say, well, let's assume that there's some kind of sub-layer profile within that follows some kind of structure to it. And so we can, one of the more common things is to do something like a linear assumption. So if you plot something in matplotlib or MATLAB or anything like that, this is kind of sort of a hand-wavy thing of what's going on under the hood. It's kind of linearly interpolating between your points, so you get a nice smooth graph as opposed to something jumpy like the left-hand column. So that kind of piecewise linear is represented in that middle panel. And if you go up one order more, you can assume that there's a parabolic shape to it, right? So a second order polynomial, something like x squared plus plus a times x plus a constant, and that gives you a parabolic reconstruction. And so that's what's kind of represented on the third panel there, where you now have this much smoother looking profile that if you were to, that looks much more like something that you would actually measure with a CTD in the actual ocean, right? So something that just smoothly varies in the vertical, as opposed to something that, like in contrast to something on the left-hand side, which is very, very jumpy. So there's a couple of terminologies I don't really want to go into, but we want these things to be monotonic so that they're always increasing or decreasing within a cell, and that these also don't introduce any new extrema. And then one last point is that we call these kind of discontinuous reconstructions because, as you can see, especially in the linear example, you can still have a jump at the interface between layers. And so that's what we call a discontinuity. So just to briefly describe the algorithm as a whole, there are three different phases of our neutral diffusion algorithm. One, we generate these polynomial reconstructions for every tracer, but particularly for temperature and salinity. For some of the examples I'm showing here, they're going to be piecewise linear just for the sake of explaining, because I don't know about you, but I can't interpolate on a parabola easily, but I can interpolate on a line much more easily. And then the next thing that we do in this initialization stage is that we calculate these the thermohaline or the thermal expansion and haline contraction coefficients at the model interfaces. And by model interface, what I mean is that if you're thinking about this in terms of a k-space and using this 1/2 indexing, an interface is that intercept, is that point where a layer of the model meets another layer of the model. So for example, if you the k minus 3/2, k minus 1/2, those are the top and bottom interfaces for the layer k of the model. We also filter out the unstable parts of the water column. I'm not going to go into that too much right now, since I think it just It's something that we need to do, but it might obfuscate the explanation of the algorithm a little bit. But if anybody's curious about why we do that, feel free to follow up. Then there's a sorting, what we call a sorting phase. And this sorting phase is when we actually create some sublayers of the model that are bounded by surfaces that are neutrally buoyant. And again, like I'll spend some time talking about that in the next couple of slides. So if you don't immediately understand what we mean by that, hopefully it'll be made clear. And then the last part of the algorithm is when we actually calculate the tracer fluxes within these sublayers. And then we have to do some limiting to essentially maintain consistency with the algorithm itself. So real quick then, just explain the figure. The interfaces, the vertical interfaces of the model are represented by this k minus 3/2, 1/2 plus 1/2, and 3/2. And then what's shown as the blue line is what a potential density would look like within this kind of hypothetical situation based on the polynomial reconstructions of temperature and salinity. So you can see that it kind of smoothly varies on the left column from the top cell and the middle cell, but then there's a discontinuity at that k plus 1/2 interface on the left-hand side before it kind of goes down. But you can see that using these reconstructions, for this particular case, the density profile is monotonic in potential density space. So, and I'm using the sigma notation here just to represent potential density, which is another simplification that I'm making for the purpose of explaining the talk. And the zeta coordinate is just a non-dimensional vertical coordinate variable that is 0 at the top of a layer and 1 at the bottom of a layer. Okay, so when we talk about neutral density or talking about the difference in density, this is the equation essentially that we're evaluating. Right, this difference in density is equal just to the difference in densities, and if you expand that in terms of the derivatives of the equation of state, what you get is that it's the average of the thermal expansion coefficients times the difference in temperature, plus the average of the halon contraction coefficients times the difference in salinity. Right, and so this will admits a lot of different things in the sense that two water parcels can have completely different temperature and salinities, but just by virtue of the fact that you have some different values for the thermal expansion and halon contraction coefficients, you can actually still have those two water parcels be neutrally buoyant. So if you use the midpoint pressure or the average pressure between the two water parcels, the institute pressure, you get basically a neutral density. This represents a difference in neutral density. If you use a single reference pressure, for example, like sigma 2, where everything is referenced to 2000 decibar, you get a different delta rho. Then is just simply isopycnal in that sense. So to find the surfaces of neutral density, we start from the top of the water column and then consecutively search down. So we look at the densities at the top interface first. So if you think that, so for example, here we have density increasing, and the scale of this is kind of that the closer you are to the right, the denser your water column is. So the left-hand column is actually lighter than the right-hand column. So we're searching down, and we know that this top interface on the left-hand side is lighter than the top interface on the right-hand side. So that holds true for all these cases except for the interface at the left-hand side that's bounded by k plus 1/2 and k plus 3/2, where we can see that this density profile, it has the same density somewhere within that cell. So this is what we mean by sorting, right? We're just kind of going down, we're finding these places where the two water columns overlap. And so this one interface on the right-hand side, this first red line with an arrowhead on it, you can see that is where the two isopycnal densities are exactly the same, right? And then so we always search from an interface. We never search anywhere else starting from it, but we can connect it somewhere on the other part of the column, somewhere in between that layer, right? And then so likewise then for the subsequent red line, this next red line, then you have it pointing from an interface. In this case, it points from k plus 3/2 on the left-hand column and points to the right part of the place in the layer of the right-hand column where the density is equal. So now we have this sublayer of the model, right, that is bounded by these surfaces where delta rho is equal to 0, that have a thickness on both sides of it. So this is what we're calling a sublayer of the model. So it's a layer. So you have these interfaces that are, or these kind of generated interfaces represented by the red lines that bound a sublayer of finite thickness. So just a couple of points. If you look at this equation, this is essentially equivalent to finding the root of a higher order polynomial. So you have to do something when a layer should connect within it. And there are also, so it essentially boils down to root finding for a higher order polynomial. There's a bunch of different simplifications that you can make in order to make the problem slightly easier. And we can discuss this at length, but for understanding the purposes of the algorithm, the only thing I really want you to know is that when we know that a neutral surface should connect somewhere between, somewhere within a layer, you just have to find out where this delta rho equals 0 somewhere within that layer. So now we get to the part. So now that we have the sublayer, we can actually calculate a flux in it. And so this is where, so this is the equation that we use to calculate that diffusive flux, right? So we have this, we have a kappa, so just a diffusivity, times an effective thickness of the sublayer, which I'll explain in a second, and then just times the tracer gradient itself, right? So what this actually looks like then on this bottom right-hand figure is that by the way that we calculate these C bar terms is by taking an average over those polynomial reconstructions. So remember that there is a polynomial representation of what the tracer concentration is in the vertical. And we average that reconstruction between the two interfaces of the model. So that's shown on the right hand panel there, where you have the C bar j k plus 1 terms and the C j plus 1 k minus 1 terms. And so that's how we calculate the tracer, the difference in the tracers there. This H effective, so this is the effective thickness of the sublayer, we calculated by doing a harmonic mean of thickness of the sublayer in the left-hand column and on the right-hand column. So the only thing really to point out in that is that this allows us to say that if the layer is really, really thin, or if the layer on one side goes to 0, then there is no diffusive flux, right? So you would never diffuse anything into a layer that doesn't have any thickness. And that's mainly the big point that we're trying to make here. But this is essentially the way that we calculate the flux within that sublayer. One thing to note in this algorithm, right, is that these sublayers can actually connect different parts of the water column. You know, so in this particular case here, the top right layer is actually connected to the bottom left layer, and you can actually then also connect multiple layers in one column to another column. So this is what's demonstrated in this slide here, and this is how we then would actually update the tracer state within a cell. So in this particular example here, we have a single layer, a single cell on the left-hand side that is actually has connected via these sublayers to two different parts of the water column on the right-hand side. But we've calculated these neutral fluxes within the sublayer, right? Oops. So there's only two fluxes actually in play here. So there's this Fn gamma flux. So that's the flux within that first sublayer. And then there's a second one within the second sublayer of the model, this Fn plus 1 gamma. And so what we essentially do is that we just add up these fluxes, add up any fluxes in the sublayers that connect at the velocity point, at the velocity face of this thickness cell here. So in this particular case, if you assume that the arrows represent both magnitude and direction, you can add this up on the left-hand column to say that Fn gamma plus Fn plus 1 gamma actually equals 0, because these two arrows are of equal length. So part of this tracer is leaving the cell, but it's also getting replenished from the other sublayer. However, on the right-hand side, the top cell will actually increase in tracer because it's getting a net flux of tracer in due to neutral diffusion, and the bottom cell will actually decrease in tracer value because it's having tracer flux out of it. So this is a really important thing to take away too, is that these fluxes can be non-local in the vertical. So for example, this sublayer can, this k equals 1 layer on the left-hand side is connecting to k minus 1 layer and the k plus 1 layer on the other side of the column. And this also demonstrates that multiple sublayers can contribute fluxes, multiple layers can contribute fluxes to a single layer in another column. And you can actually, using this algorithm, you can actually diffuse an entire column into one particular layer of the other column. So this is a really different way of conceiving how we calculate neutral fluxes. But it also does get around the problem of the rotated diffusion, because we never calculate a slope here. We're never rotating things. There's only ever horizontal fluxes that are coming into and out of a cell due to neutral diffusion. And so then I just want to close real quick to show how what this actually looks like. So we came up with a couple different test cases where we used the TIAS-10 nonlinear equation of state. This is implemented in MOM6, where the only physical process that's happening is diffusion. And we've discretized the model in two different ways. One, we've done the continuous isopycnal, and we diffuse along the modeled surfaces. And then we also have this set up as a Z-star coordinate model, where we we apply this neutral diffusion algorithm. So hypothetically, if our neutral diffusion algorithm is working perfectly, it should look like we should essentially get the same answer as the continuous isopycnal case, where we're doing diffusion along the layer. And so what this looks like is that this is basically a baroclinic looking zone where you've got where the black lines on the right-hand side show the isopycnals, and then the colored backgrounds are salt on the top panel and temperature on the bottom right. So you have these places where isohalines and isotherms are both intersect isopycnals. So if you run this to steady state or pseudo steady state, this is essentially what you get. Now this is demonstrated in this TS diagram on the left-hand side, where the black dots are the original space of the model, and then the red dots are the final state. So as you can see, when we run this steady state, now you only have a single temperature and salinity value for any given isopycnal contour. And so instead of having this envelope of TS points, you have a single line that it's all collapsed onto a single line, and that's essentially what we expect from diffusion. If you prefer to think about it based on the TNS distributions, spatial distributions, that's shown on the top right-hand side for temperature, where you can see now that those black lines, which represent the isopycnals, they have not moved in the slightest from the beginning part of from the initial state. However, the temperature lines, the isotherms, are now parallel to those isopycnals. Right, so we have this homogenization of both temperature and salinity on these isopycnals, and that's that's exactly what we expect as a result of diffusion along isopycnal diffusion. Oh yeah, I should make mention that to compare the two ways of doing it, we've actually set this to have reference pressure at 2,000 decibar, but that's purely just to demonstrate and compare against the other case. So if we run this with neutral diffusion, where we use the average pressures between water parcels to calculate the difference in density, we get very similar results. And that's actually what we end up doing in the coarse resolution configurations of MOM6. So just lastly, to close, is that we can, as I said before, like if we epipycnal or epineutral diffusion should not do any diapycnal diffusion. So we've come up with a way of trying to diagnose how much this is actually done by comparing it to a very, very high resolution isopycnal only case. And then we've run this model for both that Z-star coordinate, where we calculate it, where the model layers are all isopycnal or continuous isopycnal. And then we've done this in that second case, where we have a Z-star coordinate with constant spacing, but apply the neutral diffusion. So this is how we calculate the spurious diffusivity. But the main takeaway from this bottom right-hand line is that this black curve, this black line, which represents a long layer diffusion when the model is configured in isopycnal space, basically follows exactly on these blue dots, which is the same spurious diffusivity that you get from running our neutral diffusion algorithm in a Z-star coordinate. So just to close, this was a kind of a rather quick tour, but I hope that you took away something about how, at least conceptual, about how we do neutral diffusion. it overcomes a lot of the inherent shortcomings of the rotated operator that you just can't get around. And we demonstrated this in a limited dianeutral diffusion. I probably should have proofread that line a little bit more, but essentially we've demonstrated this in an idealized test case. So the main takeaway home from this is that instead of doing a rotated operator approach to neutral diffusion, we construct sublayers in the model where we think that are bounded by surfaces of neutral density, and then we calculate fluxes along that, and we come up with a scheme that still realizes the impact of eddies on diffusing tracers, but still maintains all these things that include monotonicity, that don't introduce any new extrema, and is still relatively cheap, though it is slightly more expensive than the rotated operator approach. And with that, I am happy to take any questions or field any clarifications that people might want.
Okay, Gökhan.
Yeah, Andrew, thank you. This is Gökhan. I had a quick question, just for clarification purpose. Sure. When you said that there is no slope limit or any kind of tapering with this approach, if you're essentially, your sorting algorithm can be such that you may be essentially diffusing from the very bottom of one particular column to the very top of the next neighboring column.
Yes, that's true. Yeah.
Right. So given that your scheme is explicit, in physical terms, when you take a water blob from the very bottom and all the way put it up there of the next row column, you may be essentially physically taking that water parcel faster than that would be allowed by the time step of the scheme. Do you have to worry about in that case, or how does the scheme take care of it, given that it's an explicit scheme?
So we don't limit the kind of that rate that it can happen. The only thing that we end up doing is that we do set a CFL limit on the diffusive part of it.
Okay.
So to essentially make sure that we don't completely deplete a cell and turn it negative.
Okay, so there is some kind of a CFL constraint that you can follow it then.
Yes, yeah. So essentially what it boils down to is that you can't, it's chosen in such a way that the tracer concentration can't go negative, but there's no, if you tried to turn it into like an equivalent advective flux, there is no limit on that. So hypothetically, yeah, you could very rapidly move from over the course of 5,000 meters. If your time step was like 30 seconds, you would still have a flux associated with diffusion. But yeah.
Thank you.
Yeah.
Okay, other questions for Andrew? Bob, did you want to clarify something?
Yes, thanks, Frank. So Andrew has hit the nail on the head. The key thing, though, is that the CFL constraint is based entirely on the horizontal grid spacing and the time step and this diffusivity kappa out front. It doesn't have anything to do with the layer structure. That's taken care of by this effective thickness over here on the right-hand side, which is, well, I guess there's a factor of 2 missing, but this is the harmonic mean that takes care of the cases where you have thin layers interacting with thick layers. So there is a constraint, but it's one that's relatively easy to calculate and apply beforehand without consideration of any of the sorting and remapping.
Okay, any final questions for Andrew? Okay, well, thanks, Andrew.
All right, thank you.
You could unshare. Let me, so next.